Hi everyone. Today we are going to understand one of the most important ideas in mathematics, that is integration. Don't worry if you have never studied integration before, as we are going to start from absolute zero. By the end of this session, you should understand not only how to solve an integration but also what an integration means. So let's begin with one very simple question. If something is changing continuously, how can we find the total amount that has accumulated? That is the central idea behind integrations. In simple words, integration is continuous addition. Let's see what that actually means. Imagine a car traveling along a road. The speed of the car is not constant. At one moment, it may be traveling at 40 km per hour. A little later, it may be traveling at 50 km per hour. Then 60, then perhaps 45. The speed keeps changing. Now, suppose I ask you, how far did the car travel during this entire journey? You cannot simply multiply one speed by the total time because the speed is continuously changing. So instead, let's divide the journey into many tiny time intervals. During one tiny interval, let's it dt, the speed is almost constant. Therefore, the tiny distance traveled is approximately speed multiplied by dt. Now imagine adding the distance traveled during every tiny interval. Tiny distance plus another tiny distance plus another and another and another. When we add all of them together, we get the total distance. And that process of adding infinitely many tiny contributions is what integration does. So we can write distance equals the integral of velocity with respect to time. This is our first important idea. Integration adds up tiny quantities to find a total. Now, area under a curve. Let's look at another example. Suppose we have a curve y equal f of x, and we want to find the area underneath the curve. If the boundary were a simple rectangle, this would be easy. We would simply use area multiplied by the breadth. But the region underneath the curved line is not a simple rectangle. So what can we do? We can divide the region into many small rectangles. Each rectangle has a very simple area. Its area is height multiplied by the width. So if we calculate the area of the first rectangle, then the second, then the third, and keep adding them. The rectangle will not fit the curve perfectly, so our answer is only an approximation. But now comes the beautiful part. What if we use more rectangles? Instead of 5 rectangles, use 50, then 500s, then 5000s. As the rectangles become narrower and narrower, they fit the curve more and more accurately. And in the limiting case, when the width of each rectangle approaches 0, the sum becomes exact. The exact process is represented by an integration or integral. So, the integration from a to b of f of x into dx represent the accumulated area under the curve between a and b. This is one of the most important visual meaning of integration. What does the integral sign mean? Now let's understand the strange looking symbol. It may look complicated at first, but its meaning is actually very simple. It means add up. The symbol is related to the old idea of a sum. So when you see an integration or integral, you can mentally read it as add up all the tiny pieces. Now what about dx? The dx represents this very small width in the x directions. Imagine taking one extremely thin slice under the curve. Its height is approximately f of x. Its width is dx. Therefore, the tiny area is f of x multiplied by dx. And the integral adds all of these tiny areas. So, integration of fx dx means add up all tiny quantities f of x dx. Once you understand this picture, the integral sign becomes much less mysterious. Integration means accumulations. Now, we can go one step deeper. Area is only one application of integration. Integration is really about accumulation. For example, if velocity is changing with time, integration or integrating velocity gives distance. If density is changing along an object, integrating density gives total mass. If a flow rate changes with time, integrating the flow rate gives total volume. And in probability, integrating a probability density gives probability. So whenever something is made up of many tiny contributions, integration can help us find the total. That gives us powerful definition. Integration is the mathematical process of accumulating continuously changing quantities. Keep that idea in your mind. It is more important than memorizing formulas. Integration and differentiation. Now we come to the most important connection in calculus. You may already have heard about differentiation. Differentiation asks how fast is something changing. Integration asks how much change has accumulated. They are closely connected. In fact, they work almost like opposite processes. Let's take a simple example. Suppose f of x equals into cubed. Differentiate it. The derivative of x cubed is 3x squared. So differentiation takes us from x cubed to 3x squared. Integration goes in the opposite directions. If we start with 3x squared and integrate it, we get x cubed plus c. Therefore, integral of 3x squared dx equals cubed plus c, x cubed plus c. This is why you often describe integration as finding an antiderivatives. Why do we add plus c? Now you may be wondering, why do we write this mysterious plus c? Let's understand it. Suppose we differentiate x squared, we get 2x. Now differentiate x squared plus 7, we'll get 2x. What about x squared minus 100? Again, the derivative is 2x. Why? Because the derivative of any constant is 0. So differentiation cannot tell us which constant was originally present. Therefore, when we reverse differentiation, we have to allow for any possible constant. We represent it by the letter c. So the integral of 2x dx equals into squared plus into squared plus c. This is the reason for plus c. It is not an extra decoration, it is mathematically necessary. Now, definite and indefinite integrals. There are two important types of integrals. The first is an indefinite integral. For example, integral of x dx, 2x dx. We're looking for an alternative or antiderivatives. The answer is x squared plus c. The second type is a definite integral. For example, the integral from 0 to 2 of x squared dx. Here we have limits. 0 is the lower limit, 2 is the upper limit. So we are asking for the total accumulated quantity between these two values. In the area interpretations, this means the area under the curve from x equals 0 to x equals 2. And unlike an indefinite integral, the final answer is specific number. For this example, integral from 0 to 2 of x squared dx equals 8 by 3. The fundamental theorem of calculus. Now we reach one of the most beautiful ideas in mathematics. It is called the fundamental theorem of calculus. The theorem connects differentiation and integrations. Suppose we have a definite function of f of dx of x whose derivative is f of x. In other words, f prime of x equals f of x. Then the definite integral from a to b of f of x dx is capital F of b minus capital F of a. In symbols, integral from a to b of f of x dx equals capital F of b minus capital F of a. Why is this so powerful? Because instead of adding thousands or millions of tiny rectangles, we can simply find an antiderivative and evaluate it at the two endpoints. This is the bridge between the geometric idea of area and algebraic idea of antiderivatives, the power rule. Now that we understand the concept, let's learn our first basic integration rule. It is called the power rule. Suppose we have x to the power n. To integrate it, the first increase the power by 1, then divide the new power. So, integral of x to the power of n dx equals x to the power n plus 1 divided by n plus 1 plus c. This works as long as n is not minus 1. Let's take an example. The integral of x squared dx, increase the power from 2 to 3, then divide by 3. So the answer is x cubed divided by 3 plus c. Another example. Integral of 5x cubed dx, the 5 stays outside. Integral of x cubed is x to the 4, x to the 4 divided by 4. Therefore, 5x to the 4th divided by 4 plus c. Substitutions. Now we are ready for an important technique called substitutions. Substitution is useful when one expression appears inside another expression. Consider integral of integral of 2x cosine of x squared or dx. At first, this looks complicated, but look carefully. Inside the cosine, we have x squared. What is the derivative of x squared? It is 2x. And we already have 2x sitting outside. That is a clue. So we make a substitution. Let's u equals x squared, then du equals 2x dx, and the original integral becomes the integral of cosine u du. This is easy. Integral of cosine u is sine u plus c. Finally, replace u with x squared. So the answer is sine of x squared plus c. The key idea behind substitution is change the variable to make the integral simpler. Integration by parts. Another important technique is called integration by parts. It is especially useful when the integrand contains a product of two functions. For example, x multiplied by e to the power x. Integration by parts comes directly from the product rule of differentiation. Now, the big picture. Let's now put everything together. At the beginning, we asked what is integrations. We can now answer the question in several connected ways. Integration is continuous addition. It is accumulated of tiny quantities. It can represent the area under a curve. It can calculate total distance from velocity. It can calculate total mass from density. And mathematically, it is also the reverse process of differentiation. The integral sign tells us add up. The dx tells us take a tiny piece in the x directions. The fundamental theorem of calculus tells us integrations and differentiations are deeply connected. And the different techniques, such as the power rule, substitutions, integration by parts, are simply different tools for evaluating integrals. So whenever you see an integral sign, don't immediately think, which formula should I memorize? Instead, ask, what is being accumulated? Once you start thinking that way, integration steps being a collection of strange symbols and formulas, it becomes a very natural ideas. Take infinitely many tiny contributions, add them together, and they find the total. And that is the heart of integration. Thank you.